Hello everyone, I am team captain of Bursa Uluda University's rover team called UluRover. UluRover is one of the largest team in Robotic Society, which is the most prestigious and oldest societies of Uluda University. We founded this team, UluRover, in 2023 where we made our first prototype called Hedger. And then in 2024 we got a chance to make our first presence in the ARC Anatolia Rover Challenge competition, where we get a chance to see the real environment and we learn a lot from our mistakes. And now, after improving ourselves and learning from our mistakes, we are excited to be a part of European Rover Challenge 2026 with a new and stronger rover called Asteroid Destroyer. So now, allow me to introduce you to my team and my beast, Asteroid Destroyer. Our team is divided into 5 sub-teams including mechanics, electronics, software, organization, and science. Our team consists of 20 members coming from different departments including sciences, social sciences, and also engineering.
I am Batu, I am the captain of the mechanical team and I have designed the robotic arm.
The robotic arm we designed, it has 5 axes. Skeleton of the robotic arm mostly made of aluminum and some part made of plastic and steel. The weight of the robotic arm around 25 kilograms. It can reach around 1 meter area. We use step motor on all axes to move the arm. It could make arm heavier but we can take too much torque from step motor. And for the power transmission we use worm gear we produced. Worm gear help us that robotic arm can stand continuously even when we cut the electricity. On the top of the arm, there are grip and derail system. We can use one of them we want thanks to system we designed.
For UluRover's mobility system, we decided to go with the rocker buggy suspension system with 6-wheel full electric drive. We decided to go with the rocker buggy suspension because it allows us to maintain constant contact with the ground and allow us to never slip. Now, we do this with a central shaft. The shaft is connected to both suspension arms that move separate ways. Now for the wheels, each wheel has a built-in DC motor with 33 Nm of torque. This allows our rover to climb steep angles and overcome the kind of challenges we may face on the ARC 26 environment. Weighing it at almost 35 kilograms, the movement system is the main body of our rover. The movement system alone has a volume of 97 by 105 by 38 centimeters cube. Now, the entire system is made almost entirely out of aluminium, except for the gears, shafts, and the wheels.
Greetings, I am Eren, and I will be introducing you UluRover's electronic and communication architecture. At the core of our system, an STM32 manages real-time movement. It drives the BTS series for our mobility system and utilizes TB66-100 and DM860H drivers for the stepper motors. By executing trapezoidal motion profiling and PID algorithms, it ensures smooth acceleration and precise positioning. For high-level tasks, we rely on Jetson Orin Nano, which handles autonomous navigation and image processing via the Z2 camera. Regarding communication architecture, our data link uses ubiquity transceivers on the 5 GHz band to prevent interference. This connects via gigabit Ethernet to the Jetson Orin Nano, handling tasks like Z2 streaming and ROS2 messaging. For manual operation, we utilize a 2.4 GHz radio link system. Also, we are in a strict compliance with national radio frequency regulations, limiting our power at 27 dBm.
Hi, I am Samet. I will talk about the rover's power system. The main power users in the rover are the DC motors for movement, the stepper motors for the robotic arm, the Milnap system, and the Jetson Orin. They need different voltage levels. To supply this power, we designed a custom PDB. It provides 4 different voltage levels and includes fuse for safety. We use a 24-volt, 18 ampere hour LiFePO4 battery, which allows the rover run for about 1 hour and 30 minutes. This system provides stable power, enough capacity for the mission, and a safe design.
Hello, my name is Sid, and I am going to tell you about our UluRover's safety features. UluRover features a modular driver that is easily removable for quick maintenance. Also, we integrated indicator LEDs and an emergency stop button to immediately stop the system if there is a problem. Based on our power calculations, we are using specifically selected cables to ensure safe power distribution.
Our drone is built on a carbon fiber X-frame. It uses 4 2212 920 kV brushless DC motors and 20 amp electronic speed controllers for precise control. At its core, there is the Pixar flight controller with autopilot firmware. It supports both manual and autonomous flying by a mission planner. Powered by a 3S Super battery, it flies for 20 minutes. A VC transmitter and telemetry module ensure stable communication and real-time data transfer.
The goal of the UluRover science team is to provide a solid, foundational scientific hypothesis to serve as the basis for the rover's activities and design. And this year's new and improved Minilab design does just that. The Minilab is a Raspberry Pi 5 and Arduino-controlled automated system weighing just 2 kilograms and measuring 45 by 15 by 30 centimeters. This compact, modular platform enables low-contamination sampling, storage, and testing while integrating the drill, chemical analysis, caching, and a weather station into a single, remotely operated dashboard.
Our sampling system uses a 3D printed PLA drill capable of reaching depths of up to 30 centimeters. Mounted on a rotatable mechanism on the robotic arm, it enables precise collection from multiple angles and delivers samples directly into the Minilab. Once collected, soil enters a custom split funnel system that separates each sample into major and minor portions for parallel testing. The minor portion supports gas evolution assays with sensors positioned above it, while the major portion is mixed with water so dissolved ions can be distributed into tubes for 3 color change tests.
A rotating drum with capacity for 9 test tubes and 1 rack moves samples in front of camera for imaging. This allows the visual output of all color change ion tests to be monitored in real time from base through the Minilab dashboard. The same camera is also used to photograph rocks for identification and geological analysis. To complement this, we developed an in-house PyTorch-based rock identification model trained on a created dataset of region-specific rock type, with accelerated onboard processing supported by the Raspberry Pi AI chip. The rover also includes an onboard weather station mounted at the highest point of the system, its antenna. This station continuously measures key atmospheric gases using MQ sensors, including hydrogen and methane, along with UV levels, atmospheric pressure, and temperature.
Together, these systems allow us to test a wide range of life detection hypotheses centered on the past or present existence of microorganisms on Mars. Over years of designing Mars-focused science missions, we found that our hypotheses consistently follow the same core logic. Test soil for habitability-associated ions through color change chemistry, support those findings through identification of rocks likely to contain those ions, and test for organic molecules through gas evolution assays such as hydrogen peroxide reactions, especially targeting compounds associated with microbial metabolism. By automating this workflow in a modular mini-lab with interchangeable chemical assays, we can rapidly adapt our science strategy from one competition to the next, whether the focus is methanogenesis, sulfur reduction, or another microbial pathway.
My name is James, and I'm the captain of the software team, and I'll take you through how the autonomous navigation works.
We have continuously improved from the last previous years, and we have improved our algorithm. And this year, we are using ROS2 as our operating system and Z-Mini as our sensor. Our pipeline follows a see, think, act loop. And it is divided into 4 parts. Perception and fusion is the first one, in which we use a Z-Mini camera and extended Kalman filter to fuse visual odometry with IMU data, which ensures that it will stay stable even in rapid movements. Then we have mapping and localization, in which we are using RTAP map, which generates a 3D cloud, which then we project into a 2D cost map. While AMCL uses the particle filters to pinpoint the robot's current position in that environment. Then we have path planning. For path planning, we are using the ROS2 NAV2 stack, which coordinates the global trajectory planning and use a local controller to dynamically navigate around the obstacles in real time. Then we have the feedback, in which we are using high-level commands translated via the differential kinematics to STM, which execute PID motor control and feeds the encoder back into the loop.